Hey everybody, Phil Zito here and welcome to Smart Buildings Academy TV episode 29. In this episode we're going to go through psychrometrics, and the reason I want to spend some time covering this is a topic that doesn't get covered quite enough, and because folks are often trying to solve temperature and humidity issues in their spaces but not really understanding what affects temperature and humidity, I figured we would cover psychrometrics before we move on to covering air handling systems. So if you didn't watch last Monday's episode 28, I encourage you to go back and watch that. Episode 28 is going to be about space control, and obviously this episode is going to be about psychrometrics. So, psychrometrics, what are they? Why do they matter to us? And what do we need to understand about them? Well, this right here is a psychrometric chart. And this chart right here describes several relationships. It describes enthalpy, it describes the amount of moisture that is in air, it describes the dry bulb, it describes the wet bulb, it describes dew point, and we're going to talk through kind of all these concepts. So at the bottom of the chart, you can see the dry bulb, and this is these straight lines going up. So I'm going to zoom in a little bit, and you can see dry bulb. And then on right here, we can see wet bulb. And where wet bulb and dry bulb intersect is going to be dew point. That is what's called full saturation. We can see enthalpy over here, and we can see our relative humidity little bands right here. So as I look at this, and you'll often hear that we want to supply 55-degree air to a space as part of discharging from an air handling unit. Why do we want to do that? Well, typically what happens is 55 degrees is that magic point at which we will usually be able to hit dew point with a cooling coil that then will subcool, down to like 53 degrees. 50 degrees. And then as that air naturally warms back up, we'll find ourselves dropping to a lower relative humidity. Because what happens is when you hit saturation, when you hit dew point, right, air in and of itself, as we can see kind of over here, right, pounds of moisture per pounds of moisture per pound of dry air. As we can see that right here, the capacity of air to hold moisture, to hold water inside it, that increases as our temperature gets higher. That's why our relative humidity of, let's just say right here, let's say a relative humidity of 20% at 105 degrees dry bulb can be, and if we go over to 75 degrees, maintaining that same amount of moisture, that's actually a relative humidity of 40% because it's relative to the capacity of the air to hold moisture. So if we're trying to cool down a space, we will typically use mechanical cooling in the case of like DX cooling or hydronic cooling, and we will cool that airstream towards dew point. And when we hit dew point, moisture can no longer be added to the air, right? It's at full capacity. And as we start to cool that air, subcool that air, what happens is we actually go down and we are wringing out the moisture because we're at saturation as we watch, as we drop here, right? As we're dropping in temperature, 55 right here to 50. If we go across, we've reduced the amount of moisture that has capacity in the air, and that's why you see condensate start to come off of your coils. And then as we heat back up the air, whether that's through mixing in the space itself or that's through some form of reheat, we see that as we go back across, maybe we reheat it to 60, we are now at a different relative humidity level than we were previously. So that is how we remove humidity from the air. And that's why it's really important for us to understand what we're doing. In the case of a VAV air handler, we're driving for that 55-degree DAT because in reality, we're at anywhere from 48 to 52 at the coil, right? So at the coil, when we're leaving the coil, we're at 48 to 52 degrees leaving that coil, and so we're wringing the moisture out of the air. It's also important for us to understand that when we bring in outside air, it's not just dry bulb that we're concerned with, right? Dry bulb is just our ambient temperature. We're not just concerned with dry bulb bringing in outside air. We're also concerned about how much enthalpy, so what is the amount of BTUs per pound of dry air that is in that air? So what is the moisture content of the air? So if I go and I have a choice to use a return temp, right, of let's say 75 degrees at 30% relative humidity or 65 degrees at 50% relative humidity, and that's outside air, I am introducing significantly more moisture back into my airstream, and that will make people feel muggy, it'll make people feel hot, it will make the transfer and the cooling less effective because we're introducing more enthalpy. That's why you'll see enthalpy used as a comparison for economizer enable. You'll see dry bulb and you'll see enthalpy. So when you're comparing dry bulb, you're just looking and saying, hey, am I greater than 55 degrees, and am I less than 80 degrees? Okay, if so, enable my economizer. That can work in some regions of the United States and of the world, but when you get into very humid regions, you want to compare enthalpy. You want to look at what is your return enthalpy, what is the amount of BTUs in that air, and then what is your outside air enthalpy. And you want to decide which one is greater because that has a load effect on your system. So let's recap on what we've discussed so far. We've talked about the psychrometric chart, that's this right here. Dry bulb being along the bottom, you can see these straight lines going up. We can see our enthalpy lines coming diagonally across. We can see our relative humidity lines right here. We can see that we have our dew point line, right? We see that right here, our dew point. We can see the amount of moisture per pound of dry air, right? Over here, so the capacity of the air. And as we go and think about, like, let me see if I can bring this up for you. As we look at a psychrometric chart, remember I said cooling, we are going to be going across the psychrometric chart. So let me just kind of show you. Cooling, we're going to go across, we're lowering dry bulb, and that effect of lowering dry bulb is going to bring us closer to dew point. And as we get closer to dew point and saturation, if we continue to cool and we continue to drive dry bulb down, then we will start to condense and we will start to remove moisture out of our airstream. So that's dehumidification as well as cooling, right? Now we see up here humidification. That's adding moisture to the airstream. That's just going and increasing the amount of pounds of moisture per dry air, typically with something like steam, although you can use other forms of humidifiers as well. And that is just straight up. You are straight up increasing the amount of moisture in the airstream. Dry bulb should be remaining the same. Obviously, if you're using steam, you could see an increase in dry bulb at the same time, depending on what kind of steam you're using and how you're using it. Then we see heating. Heating is also going to be going across dry bulb, and that is also a way of lowering the moisture level of the air. Although you're not really lowering the moisture level of the air, you're lowering the relative moisture level of the air. I want to be clear on that. The only way you are truly lowering the moisture content of the air is driving the air to saturation with dew point or using some chemical decusant, I think. Yeah, if I could say the word right. But you drive to dew point or you use decusant, that will actually remove moisture from the air, either through condensation or, in the case of decusant, absorption. So you'll have absorption of the moisture, and then it will be transferred out like typically in a decusant wheel. With heat, you are not removing moisture, you're just lowering the relative effect of moisture, because remember, as we increase our air temperature, the capacity of the air to hold moisture is reduced. So that is going to be, you've got the same amount of moisture in the air, but relative to that air's capacity, it's lower. And then finally, we can see, right, we see dehumidification, humidification, cooling, and this is the mechanical, chemical effect right here. So that, my friends, is psychrometrics. It's a very, very important thing to understand. This has saved my butt so many times when I've been out in the field and I've had to explain to engineers or I've had to explain to customers why the control strategy they're implementing is not going to work, as well as what potential changes they can make to their control strategy. Understanding that mechanical cooling drives us to saturation, drives us to dew point, and then we continue to subcool, and then we actually remove moisture in the form of condensate. Super important to understand. Understanding that heating does decrease relative humidity, but it does not decrease the moisture amount in the air. Understanding that chemical removal of humidity can be done without affecting dry bulb in the form of decusant, and that we can add humidity to the airstream, potentially not affecting dry bulb depending on our humidification. If you get this, if you understand this one chart, it will help you substantially. If this is something that has been interesting to you, I encourage you to check out our Control Sequence Fundamentals course at courses.smartbuildingsacademy.com. I will link to that. This is just one of the topics that we cover in great detail in that course. I encourage you to use coupon code TAXDAY until April 15th. All courses are 20% off, so definitely take advantage of that. And if you have any questions related to psychrometrics, I really would love you to ask those right now. Like, just ask away. This is a super duper important topic, and I guarantee you a fair bit of your peers do not know how to read a psychrometric chart. They don't understand the interrelationships between temperature, humidity, dew point, dry bulb, enthalpy. And without understanding these relationships, both on the engineering side as well as on the troubleshooting side, you can find yourself really struggling to just accurately drive your building automation systems and your HVAC performance. So please do not hesitate to ask me any questions you got. I'd love to hear from you. And with that, I'm gonna switch screens real quick. Alrighty. So what can I answer for you around psychrometrics? What questions are you curious about? What can I cover for you? Let me know. I'd love to know. And I got another question for you all. Does this time work better for you, or does 8 p.m. on Wednesdays work better? I created this time so that the folks in Europe could attend without it being like crazy late for them. But that being said, if 8 p.m. works better for the majority of the audience, let me know. And by the way, make sure you hit the subscribe button and hit the notification bell. That way you get notified when we do new videos, even though these videos are pretty much every Wednesday at 11 and every Monday at 8 Central. Sometimes we do change the times based on just what's going on in life. That being said, let's take a look real quick. Coming up, we are going to have airside systems, and that is going to be on Monday. And so airside systems is going to be about rooftop units, air handling units. We're going to talk about safety circuits. We're going to talk about economizer. We're going to talk about cooling and VFD control. Then we're going to go into pressure control. We're going to talk about space pressure. We're going to talk about building pressure. We're going to talk about stack effect, all of those things, volumetric offset and matching. Then we're going to move into chilled water control on, well, that'll be the following Monday, so the 19th, where we'll go through air-cooled chillers, we'll go through water-cooled chillers, we'll go through cooling towers, we'll talk about plate heat exchangers, we'll get into a little bit of pumping, primary, secondary loops, decouplers, and then finally we will move into hot water control, where we'll talk about boilers, both normal hot water boilers as well as domestic, and we will talk through steam and tubular steam heat exchangers and 1/3 and 2/3 valves. So that is the plan as we continue this HVAC series on psychrometrics. I really encourage you to share this with your peers. If you all could do me just one favor, if you could tell 3 people, just 3 people about this live stream and encourage them to attend on Mondays and Wednesdays, that would be super helpful. It's just, it's really valuable information based on y'all's feedback, and the more eyeballs we get in front of it, the better. So what is the best practice to disable economizer to prevent indoor mold growth in humid areas of the country? Outdoor air dew point lockout, outdoor air dry bulb temp lockout, outdoor air enthalpy. Well, when you're saying indoor mold growth, I assume you mean within the spaces themselves and not necessarily within the units. Because within the units, you can solve that with UV lighting. So what I like to do with outside air is I like to do enthalpy in humid areas, because enthalpy is going to give you a really good look at what your return humidity load is. Because remember, and I'm going to transition us back here. I'm going to kind of transition us over here. Remember that enthalpy, right, is the BTUs per dry air, but it directly correlates, if we look at it, it directly correlates with kind of dew point. And then as we go across, we see that dew point is directly correlating with the amount of moisture that is in the air and the air's capacity to hold moisture. So if you compare enthalpy, and you can do that by just doing relative humidity and the, what's the enthalpy calculation again? Off the top of my head, if I remember correctly, it's relative humidity and dry bulb. I'll look that up. Let me take a look. So, enthalpy calculation. Yeah, enthalpy is M times S times delta T. So, yeah. Or you just throw it in an enthalpy calculator, which is what I always did, so I never memorized the enthalpy calculation. That being said, I like that, personally. You can also look at space humidity and use that, return air humidity, and you can use that to drive your economizer. It also depends if you have a way of removing moisture in the airstream and whether this is 100% outdoor air or it's a mixed air unit. So assuming it's a mixed air unit, and assuming you have to keep, 5-10% damper position open in order to satisfy ASHRAE 62.1, then in reality, from a moisture control perspective, you can add a decusant wheel. That's one strategy. You can add a humidification strategy with reheat, subcooling, and then reheating. That's going to be inefficient from an energy perspective, and your system may not be sized to do that. As far as how you go and sequence it, like I said, you can look at return air humidity for load. You can look at return air enthalpy versus outdoor air enthalpy. You can have a cutoff when your spaces, because if I remember correctly, it's 60% relative humidity and greater within the space is likely to do mold, and then 70% or greater is like, yeah, you're going to get mold. So that's what I would look at. Hopefully that helps. What other questions can I answer for you all? And just remember, dew point lockout and enthalpy lockout are going to basically be the same thing, although they're different numbers. They're affected by the same thing, right? We see dew point, and the thing with dew point that you have to realize, this is the last thing I'm going to add, is that dew point may be at saturation and cause condensation inside your equipment. But as you start to mix that air at dew point back with an airstream that is within the space, you're going to be moving this way right? You're going to be moving to the right across the chart. And as you do that, your relative humidity is going to drop substantially, especially when you get into the 70 range. Right here in this 50 to 60 degree dry bulb window is where you see a lot of relative humidity buildup. But as you move past this 65 degree dry bulb, you start to see the bands get pretty large between here. And it's okay to have moisture in a space as long as you're far away from dew point and it's not condensing. That being said, certain porous materials can absorb the moisture, so do be cognizant of that. But your real concern should be condensation and buildup of like subcooled areas, like a subcooled plenum, or walls that are maybe exterior exposed and they get cold during the day. Brick is notorious for this. A lot of these older buildings with brick walls, and it gets cold at night and those walls retain that temperature and they stay cold, and you'll see the walls will just feel slick because of that condensing effect, because those walls are lower temperature than ambient. So probably way more information than you wanted to have, Charles, but hopefully it helps. I hope it's useful. All right. What other questions can I answer for you all today? All right, not seeing any. I will leave you all with this. If you've at all considered our courses, I really encourage you to take advantage of our tax day sale. We've had so many people who have gotten promoted and gotten raises and gotten hired through our training courses. And all of the 20% discount disappears on the 15th. So you got about a week left. So definitely feel free to go and check out our courses at courses.smartbuildingsacademy.com and use that tax code or the discount code TAXDAY. That being said, thanks so much for being here. I look forward to all of you continuing to engage. Like I said, all I ask is that you share this with 3 people so that they can also come and engage in the conversation and lessons every Monday at 8 p.m. Central and every Wednesday at 11 a.m. Central. Thanks a ton. So awesome to have you all here. And I look forward to talking to you all in next Monday's live stream. Thanks a ton. Take care.